Hi, everybody. I'm Wolf Dobson, and I apparently can't walk upstairs. No, I'm Wolf Dobson. I'd like to talk to you today about the frontiers of TensorFlow. So this talk's got three parts. We're going to talk about the latest developments in TensorFlow. We're going to talk about Cloud TPUs and TPU pods. And finally, Zach's going to tell us about the TensorFlow Research Cloud. OK, so TensorFlow. It's machine learning for everyone. We like to say that it is fast, it is flexible, and it is production ready. When we say production ready, what we mean is the code that you mess around with on your laptop, that you try out on your local machine, it's the same code that you push out to run on giant clusters. It's all the same thing all the way down, no rewriting in a new language after you figured it out. So TensorFlow is this language that allows you to write computational graphs. And you use these computational graphs to do usually machine learning and often deep learning. So here's an example of sort of a basic deep learning graph. Here we have a picture of a cat or a dog that we feed in as pixels into the convolutional layer at the bottom. And then it convolves all the way down to give us a prediction of some kind. Either it's a cat or it's a dog. Convolutional layers are one kind of thing. This is another kind of thing. This is a collection of fully connected layers where we have each node on each layer connects to every other node on the next layer. The arrows between those are all weights. Those weights are, we like to call them parameters, and they get changed over time. This is a very deep network where this is Inception v3. Inception v3 has about 17 layers, depending on how you count. And it has about 25 million parameters. So it can take a while to train. And so what do you do when you're writing TensorFlow? You're writing probably Python. And you're going to knock out some Python there, and it's going to generate this graph for you. And then that graph, you're going to execute later. And you're going to execute it in two ways. One, you're going to be doing training, which means that you're going to be showing it examples and modifying, based on the results you get, modifying those parameters. And then when you can run it again later on new data. We call that inference. And we're hoping to get some kind of statistical insight out of all the data that we have onto this new data. TensorFlow runs on all kinds of platforms, CPU, GPU. Obviously, we're going to talk about TPUs later. They're pretty neat. And also on mobile, iOS and Android, and actually also on Raspberry Pi. Raspberry Pi is fun. You can actually compile all of TensorFlow on Raspberry Pi. And we support all kinds of languages. TensorFlow, Google supports Python, C++, Java, and Go. These others are all community projects. We're really excited about the community picking these up and using our low-level C bindings to create new language wrappers. And TensorFlow comes with a lot of different kinds of tools. This tool is TensorBoard. TensorBoard is sort of like X-ray for your training process. It allows you to look inside your training and see what's actually going on inside your graph. It lets you inspect your graph. And in this case, we're even showing off an embedding. That's MNIST, for those of you who recognize it. It's handwriting data. And you can see we're kind of grouping all the 5s as gray and all the 9s as red. It's really neat to be able to look and see what's actually going on. And once you've got this all trained up and you want to push it into production, we have TensorFlow Serving. TensorFlow Serving is a separate open source project, also developed by Google, that lets you kind of manage the process of serving a model in production. And it lets you do things like serve multiple models in production, use it with some kind of container engine like Kubernetes. It allows you to manage the process of setting up one of these big services that will allow you to do insight for your customers. There's a great talk about this. I encourage you. Noah Fidel is going to be speaking about it on Friday. So inside Google, TensorFlow is very popular. This is a graph of directories inside Google with model description files in it, which is to say, this is like a little piece of machine learning that we have inside our main Google repository. And you can see TensorFlow launched in Q3 2014 internally. We actually had another system before this. It was called distbelief. Distbelief was great. It wasn't quite flexible enough for the kinds of projects that we wanted to do. And you can see, after we launched TensorFlow internally, there was this kind of explosion of trying to apply ML to every kind of problem at Google. Search, Gmail, Translate, Maps, all kinds of stuff. And in November 2015, we launched TensorFlow in public. There we had it quickly became one of the most popular, actually the most popular machine learning GitHub project. And when we say most popular, we mean really most popular. This is a graph of all of our stars over time. We're really happy about community. And speaking of community, since November 2015, we've had 17,000 commits in public, many of those from external contributors. We have almost 500 non-Google contributors for TensorFlow version 1.0, which we cut in February. And we've actually had some very significant external commits. One that comes to mind is the Windows GPU support. It was actually external, and it was committed in, and we absolutely loved it. And if you hunt around on GitHub, you'll find thousands of other repositories that have TensorFlow in the title. And along with that comes blogs and books and all kinds of other materials that, again, the community is putting together, and we're so happy that they are. We also take supporting TensorFlow seriously. One of the great things about working on the TensorFlow team is our engineering team actually takes rotations through Stack Overflow and the PR and also issues and PRs. So we've had over 5,000 Stack Overflow questions answered, and again, about 5,000 GitHub issues filed and triaged in some useful way. And we have a lot of activity. We're getting almost 160 new issues a week. So where are we today? Last night, or actually yesterday afternoon, we branched TensorFlow 1.2. There's a lot of new stuff in Tensor 1.2 around supporting TPUs. And Brendan's going to talk about that. But something that's come into TensorFlow recently is XLA, which is TensorFlow's compiler for accelerated linear algebra, XLA. And basic idea is TensorFlow graphs go in, and optimized assembly comes out, machine code that will actually run. It's not like an optimized version of the graph. It's like it is an optimized version of the graph, but it's actually running in machine code. Super important to support custom hardware, and again, we'll talk more about this with the TPU section. TensorFlow is a distributed execution engine that runs on top of all these other kernels for iOS, Android, GPUs, CPUs, all that kind of stuff. On top of that, we have the Python front end, which is how you program it. We have a C++ front end as well, and all these other languages. Recently, in TensorFlow, we've added Layers API. And Layers API gives you sort of big building blocks that are the right shape for you to do basic machine learning tasks in the kinds of ways we've done. Convolutional layers, fully connected layers, all that kind of thing. And on top of that, we have both Keras and estimators. Keras is an API that actually didn't originate at Google, but we liked it so much. It's actually in Contrib right now. Keras is a high-level API that gives you even sort of easier, powerful ways to fit all of these different all your graphs together. And then it's actually built on top of our Layers API as well. And then we also have estimators. And estimators are a way to package up and abstract away sort of the concepts of machine learning. It has fit and estimate, fit and evaluate and all the rest of that stuff. Again, estimators are really important for parallelization. And with estimators, we've even come with canned estimators that are going to help you if you just have some data and you want to do a simple linear regression or linear classifier or a bunch of fully connected layers, whatever it is that you want, we might be able to give you a canned estimator that allows you to do no graph construction and just drop your data in and go. The effect of all these high-level APIs, like Keras and canned estimators, one of the things you're going to see is code gets smaller. But beyond that, like I said, a big thing about estimators is they help you parallelize your computation. And we're going to talk about that more, because TPUs are super parallel. Speaking of performance, let's talk about performance. About a week and a half ago, we released a bunch of benchmarks. They're actually on TensorFlow.org. There's a link down there. This is one of the graphs on that page, an NVIDIA DGX1 running on synthetic data on 1, 2, 4, or 8 GPUs. And there's a lot of raw throughput there. You can see a whole bunch of images per second. Images per second, super important. Another thing that's really important in machine learning is that you get good scale up. What that means is if I add another GPU, do I get another GPU's worth of performance out of that? So in this graph, if you go from 4 to 8 GPUs, do you actually see double the performance? It's a little bit hard to read on this graph, so we made it a little bit easier. An ideal scaling line on this graph, and this is GPUs on one axis and speed up on the other, and you'd want, with one GPU, you have 1x speed up, and 8 GPUs, you have 8x speed up, and you want a straight line all the way down there. And on our test data, which are common models in machine learning, Inception, ResNet 50, you can see we're getting pretty close. On the left is synthetic data. Synthetic data is when you're kind of holding your inputs more or less constant, and you're just putting the engine on cinder blocks and just revving the engine as fast as you possibly can. At Google, we think it's kind of important to try it with real data as well. So on the right, we have the same test except with real data. And you can see it's not quite as ideal. It's never going to be ideal because there's going to be overhead for doing the parallel computation. But we're getting pretty close. And if you want to scale out to lots of GPUs, we have benchmarks for that as well. This goes out to 64 GPUs, this time on K80s in the cloud. Again, you're looking for that, from 32 to 64, are you getting double the throughput? But don't take my word for it. Try it yourself. Not only did we release the page that has all these benchmarks and graphs on it, we also released the code. So you can download it and run it yourself on your own setup. And we have benchmarks on NVIDIA DGX1, Google Compute Engine, Amazon EC2. But please, try it on your own setup and tell us how it goes. Also, that code is tuned for speed. And so it's a good place to look that if you're having issues with scale up, you can take a look at our stuff and see how we did it and see if that can help you. But 64 GPUs is a lot, but there's more than 64 GPUs. And with very large compute, with very large models, you're going to need a lot more computation to train them. And that kind of computation is more powerful chips, faster communication among accelerators, better, faster memory, and a fully optimized software stack. So to tell you about that, tell you about TPUs, which are all of those things, I'm going to hand it off to Zach.
Thanks, Wolf. I'm super excited about TPUs, and I'd like to share the story of their development with you today. So some of you may remember this image here. This is an image of Google's first generation TPU, which Sundar revealed at Google I/O last year. Google actually considered building custom ASICs as early as 2006, but the situation got more urgent in 2013 when one of our star engineers realized if all Android users spoke to their phones for just 3 minutes a day, that might force Google to double its number of data centers. So that drove this crash project to develop our first TPU, which in just 15 months of building and deploying these in the data centers brought us to some pretty significant performance gains across search ranking, Google Photos, Street View, Google Translate, and a variety of our other large-scale machine learning applications. In fact, compared to contemporary CPUs and GPUs, this first-generation TPU was 15 to 30x faster on these internal workloads, while being 30 to 80x more power efficient. But there was an important limitation, namely that this first-generation TPU was designed for inference, not training. As Wolf mentioned earlier, training is this enormously complicated process of setting all those weights in these giant machine learning models. And then inference is the process of running the models. And so while the first-generation TPU was fantastic for running models that had already been trained, Google still needed to use other hardware, huge clusters of CPUs or GPUs, to train these models. That inspired the development of our second-generation TPU, which is what Sundar announced yesterday. This device delivers up to 180 teraflops of floating point performance and contains 64 gigabytes of ultra-high bandwidth memory. The most important thing about this new second-generation TPU is that it's designed to support both training and inference on one platform. And that turns out to be really convenient, because it allows you to develop your model and then run it in exactly the same way. You don't have this barrier of friction of having to quantize the weights or figure out how to deploy it on a separate platform. But for some of Google's largest scale machine learning problems, even 180 teraflops isn't enough. And so from the beginning, these second-generation TPUs were designed to be connected together with an ultra-fast custom network. We call these collections of TPUs pods. And the TPU pods that you see here contain 64 of these new second-generation TPUs. If you add all that up, that gives you up to 11.5 petaflops of machine learning acceleration that you can apply to a single machine learning training problem, or you can split up to support many different training problems in parallel. This whole system has 4 terabytes of memory, and the TPUs are connected in a toroidal mesh network, which facilitates the ultra-fast, ultra-dense communication that you need, especially to solve these machine learning training problems. We're already seeing interesting results on some of the important internal workloads that matter to us. For example, on one of our new large-scale neural machine translation models, it used to take us 24 hours to train this model on 32 of the best commercially available GPUs. Now, in just 6 hours, we can train to the same accuracy on 1/8 of a TPU pod. These new devices, these second-generation TPUs, we're thrilled to announce are coming to Google Cloud as Cloud TPUs. Our goal is for Google Cloud to be the best cloud for machine learning. So we offer customers the choice of the best hardware that you can find anywhere, whether that's Skylake CPUs, NVIDIA's GPUs, we're planning to introduce Volta, and now this new member of the family, Cloud TPUs, so customers can build the best machine learning systems for their specific workloads. To tell you a little bit more about how Cloud TPUs are going to integrate with TensorFlow, I'd like to hand it off to Brennan.
Thank you, Zach. Today, I want to talk to you about Cloud TPUs. Now, as we've designed Cloud TPUs, we wanted to ensure that it would meet your needs, whether you are a researcher or whether you're designing a high-scale, high-performance machine learning product. And so for researchers, we wanted to ensure that it was interactive and low-level. You can play around with your models and debug them. And for high-performance, high-scale platforms and products, we wanted to ensure that it would integrate with the rest of Google Cloud Platform. But I think that instead of me just telling you about it, it's more exciting if I show you. Now, before I show you, I want to say an important caveat. As we bring TPUs to Google Cloud, there's a lot of moving pieces, and so some of those pieces are still under active development, so things may change. That said, let's get started. The simplest model that I think I can show you is alpha times x plus y. So alpha is the constant 2. X is a vector, or we call a tensor, of 3 ones. Y is also 3 ones, and we hope to, at the end of this computation, get 3 3s. In order to use Google Cloud TPUs, you've got to first create one. When you create one, this is your Cloud TPU. And so in order to access it, however, you need to access it via Google Compute Engine. So we first create a virtual machine in Google's Compute Engine product, and we're going to name it Demo VM. Additionally, we're going to create a TPU, and we're going to call that Demo TPU. If we then log in to our Demo VM, this is what we could see after we installed TensorFlow. So we're going to run the Python interactive interpreter, and we're going to import TensorFlow just like normal. After that, we're going to connect to our Cloud TPU using gRPC, Google's open source RPC framework. After that, you use TensorFlow just like you normally would, whether on a CPU or a GPU. The only difference, however, is that you define your computations that you want to run on the TPU in this with tf.device block. In doing so, you tell TensorFlow to run the computation on the TPU. After that, you can just run it, again, just like normal TensorFlow, and it just works. It's very exciting. So to review what just happened, we logged into our Google Compute Engine VM. We ran our TensorFlow and our Python interactive interpreter. We connected to the Cloud TPU and ran our computation on the Cloud TPU and fetched the results back into our Google Compute Engine VM. But this one VM and one Cloud TPU is really only the beginning. We've designed Cloud TPUs to integrate with all the rest of the hardware and compute platforms available in Google Cloud Platform. So if you have a model that part of the model runs really, really well on brand new GPUs, and part of your model runs really, really well on Cloud TPUs, you can create your own esoteric heterogeneous cluster and place your model so that the right parts of the computation run on the right compute nodes. But one thing we've learned at Google is that as you push the boundaries of computational power, as you push extreme scale, you need to optimize the entire system from end to end. And what I mean is, you need to take into account not just the amount of disks that you use to feed your data quickly into these accelerator pods, and not just the network that connects all of these distributed machines together, but you also need a highly tuned software platform. And to tell you about that, I'd like to tell you about some of the latest changes that are happening that are still under active development in core TensorFlow. Now, previously in the presentation, we had a picture of the core TensorFlow platform. And I've redrawn that, adding a few extra boxes. And I'm going to talk to you today about XLA, estimators, and datasets. Let's start with closest to the bare metal. Let's talk about XLA. TensorFlow is designed to go from research to production. And production means not just servers in a data center, but it means going all the way from phones to these exotic hardware compute devices like TPUs. And in order to run efficiently and to get the extreme performance, you need a highly tuned software stack. As it turns out, in order to get optimized code, you need to bring your own compiler. XLA is TensorFlow's compiler. XLA stands for Accelerated Linear Algebra. And what it does, when you use TensorFlow, you define your computational graph. And XLA will take a subset of that graph, or maybe even the whole graph. It will run a huge number of optimization passes over it, and it will output exactly the machine binary to run on the hardware that you're targeting. In this example, we're taking the inception algorithm that does extreme performance on image recognition, and XLA will take a subset of that graph, and it will reorder the computations and output the assembly in binary form to run efficiently on CPUs or GPUs. But XLA was designed for the explosion in exotic hardware that we see in machine learning. XLA has a pluggable backend so that you can target your own hardware elements. TPUs are just a custom backend for XLA. And in doing so, we take advantage of all the optimizations that we do for CPUs and GPUs, and we're able to run them also on TPUs. But XLA runs sort of underneath the hood, and so it's sometimes a little hard to see. So if you'd like to see XLA in action, you can turn on tracing when you run your TensorFlow computation. And if you print out the trace information that's stored in that run metadata object, you might see something like this. In one of the node stats, we see this funny _XLA launch operation. If you're not using XLA, the node stats will be your TensorFlow graph nodes. But what happens when you use XLA is the XLA compiler generates that optimized binary, and the XLA launch operation is the time spent actually running that binary on your compute devices. But one thing that's interesting is the node names don't correspond necessarily with your TensorFlow graph. And the reason for that is that XLA performs whole program optimization. If you've ever used an optimizing compiler and looked at the assembly that's output afterwards, you'll notice that it doesn't necessarily match up with your statements that you write in, for example, C. That's because the optimizing compiler is doing a number of tricks underneath the hood to get optimal machine performance. And XLA is doing that not just at the function or the operation level, but it's scheduling whole programs to run efficiently. So we've talked about XLA, or how you run on these new hardware platforms all the way across the range of devices we support. But I now want to talk about how you actually write your algorithms so that they can run across all these platforms. And for that, we have estimators. Now, this code snippet I'm showing you is copy-pasted directly from our source repository, and it runs today on CPUs and GPUs, and I'm going to show you how we can modify it to run on TPUs. When you use estimators, you define your machine learning algorithm using a model function. And this is the model definition for a simple convolutional neural network to recognize handwritten digits. This is the MNIST dataset, for those of you who are familiar. I want to draw your attention to the final 3 lines. And in order to see them a little bit better, we've made them a little bit bigger. Normally, when you train your machine learning algorithm, you use a gradient descent optimizer or similar to optimize the weights. This is the training step of your machine learning algorithm. In order to get it to run on TPUs, you just wrap your gradient descent optimizer with a TPU cross-shard optimizer. TPUs have a number of parallel compute elements that all work together. And in order to aggregate the learned weights, you need to use this cross-shard optimizer to relearn the entire algorithm. That is the only change required when you're using estimators to run on CPUs, GPUs, and TPUs for this example. Now, how do you actually run it? You've got to define your main function. And using estimators, it's very simple. Normally, you just define your estimator based on your model function, and you call train. And to get this to work on TPUs, you just use a TPU estimator and use a TPU run config. That's it. That is all the changes required for this model to work on CPUs, GPUs, and TPUs. Some more complicated models may require additional code changes, but the TensorFlow team is constantly working to reduce the amount of code changes required as you go all the way to production on all these different platforms. If you'd like to hear more about these high-level APIs, I encourage you to check out the talk in the next hour about TensorFlow with the high-level APIs. So we've talked about how to define your machine learning algorithms, and we've talked about how they execute on hardware devices, but we're missing one key thing. The machine learning triad that has resulted in this explosion of progress has been fueled by 3 components: high-performance computation, advances in algorithms, and also input data. Without input data, all the fancy acceleration you want is not going to generate any more than random numbers. Cloud TPUs are designed to integrate with the rest of Google Cloud Platform to make it easy to load data in a high-performance way. You can load data from your persistent disk or your ephemeral local SSD on Google Compute Engine. But you can also stream data in directly from Google Cloud Storage into your Cloud TPUs. And for those of you doing advanced reinforcement learning algorithms or other sorts of things, you can run simulators on Google Compute Engine and integrate that with your machine learning model running on your Cloud TPUs. But as it turns out, we at Google, we've been deploying these high-performance accelerators, CPUs and GPUs, for a while. And we've found that when you really put them into production, you find new bottlenecks. And I think this is best explained with an example. If you've optimized your software platform, you'll often use pipelining techniques to overlap computation. And that's what we've done here. For this image model, we run some input processing on the CPU for the next training step, while our accelerator is running the model and learning on the current training step. But if you all of a sudden just take this and port this over to an accelerator that's 10 times faster, your training step time is not going to decrease anywhere close to what you'd hope. To help you feed data in a flexible but high-performance manner, we're introducing a new API in TensorFlow 1.2 called Datasets. TensorFlow 1.2, the first release candidate, is coming out as we speak. And we encourage you all to try out these new APIs, kick the tires. Although they're still a work in progress, we think they're very exciting. And I'd like to show you a little bit about what this Dataset API looks like. Here's a code snippet where we load a set of data from a TF record file on disk. We then repeat that data set as we train our algorithm. We perform some parsing and distortions to this using the parser function, but we can do this in parallel using the parallel num threads, so we do a parallel map. Finally, we batch this up into training bunches that we then feed to our accelerator. This new Datasets API borrows from functional programming and other advanced concepts to make it easy to define high-performance input pipelines that run well. We've talked about now XLA, estimators, and datasets, and these are just some of the new changes that are coming in TensorFlow 1.2 that help make these high-performance accelerators, be they CPUs or GPUs or TPUs, really sing. And on top of this base of awesome compute and infrastructure, we see some really phenomenal learning and research work. And for that, I'd like to turn it back over to Zach Stone to talk about research on the frontier.
Thanks, Brennan. We've witnessed extraordinary breakthroughs in machine learning research over the past several years. And while there are many types of machine learning, many of these breakthroughs have been concentrated at the edges of what's computationally possible. And we believe that much larger amounts of computation are going to unlock new discoveries and new breakthroughs, which, with larger and more complex models than researchers can practically experiment with today. In the photo behind me, Wolf's daughter represents the machine learning research community. The mountain represents the breakthroughs yet to be discovered, and that gate is the computational limits that are holding researchers back. Our goal is to break open that gate and help researchers climb that mountain to unlock new discoveries. That's why I'm thrilled that Sundar announced the TensorFlow Research Cloud yesterday in order to support open machine learning research worldwide and help researchers who currently don't have access to enough computation experiment with much larger and more complex models. We've dedicated 1,000 of these new Cloud TPUs to accelerate open machine learning research. We're going to set up an application process to let people from all backgrounds and all fields of expertise propose projects to take advantage of this extraordinary amount of computing power. This is 180 petaflops of compute altogether, and we can't wait to see what new discoveries people are going to do with this level of compute. What might those be? Well, we're looking forward to finding out. But just to highlight one example that Sundar also mentioned yesterday, I'd like to mention AutoML, which is a family of techniques for using machine learning models to develop new machine learning models. I won't go through the details here, but these are just two examples from a linguistic problem and an image recognition problem where we've used a machine learning model to generate the architectures that you see here on the screen. And the interesting thing about it is that both of these models look kind of complex and organic. They don't necessarily look like the thing that a mathematician might have come up with by hand. Now, this kind of experimentation requires immense amounts of compute, but fortunately, with this step function to Cloud TPUs and eventually to TPU pods, we want to shift the whole research mindset from scarcity to abundance, so you can start contemplating these kinds of techniques to search for new model architectures and open up new applications. So just to be clear, we have one underlying product in Google Cloud, which is these new Cloud TPUs on the Google Compute Engine. But we're offering the community access to them in two ways. For general use, we're setting up a Cloud TPU alpha program that lets businesses, startups, individuals, students, people, artists, anyone who's interested in this frontier of machine learning to sign up and try and get early access to these limited numbers of Cloud TPUs to figure out how to adapt them for their applications. But for those of you out there who are doing cutting-edge machine learning research, who are extending this frontier, we've set up the TensorFlow Research Cloud. And we're going to open up this application process to invite you in to take advantage of these 1,000 Cloud TPUs to do things that just aren't feasible today. If you're interested in either of these programs, we encourage you to sign up now at g.co/tpu-signup. Optionally, tell us more about your compute needs, and we'll notify you as soon as more information is available about Cloud TPUs and the TensorFlow Research Cloud. Now, before I go, I'd like to encourage you to either stick around for the next session, which will cover TensorFlow for non-experts and tell you more about the high-level APIs that we described earlier, or join us in the office hours section for office hours. And if you're worried, how do I choose between the next session and office hours? Don't worry. We've added a next office hour after the next session, so you can do both. Thanks again for your attention. We're really excited about TensorFlow and Cloud TPUs, and we look forward to speaking with you in office hours.